What if artificial intelligence could not only solve incredibly complex math problems, but actually prove them with perfect logical rigor, just like a human mathematician might?
It's a fascinating question.
Yeah. And today we're diving deep into Goedel-Prover-V2. It's a groundbreaking new series of open source AI models. And they're really advancing the field of automated theorem proving.
They absolutely are.
You've shared some fascinating sources on this, and our goal for this deep dive is basically to distill the core innovations. What makes these models so powerful. We'll explore their performance, which is pretty remarkable, and try to understand what this means for the future of AI, maybe even how we approach mathematical discovery itself.
It's definitely an exciting area. Automated theorem proving, ATP, it's long stood as a significant challenge for AI. It's not like generating natural language text.
Right.
ATP demands constructing these step-by-step, machine verifiable proofs, often in formal languages like Lean.
Lean. For anyone maybe not familiar, that's like a specialized programming language for math proofs.
Exactly. It's designed specifically for writing and verifying mathematical proofs. It demands a completely rigorous logical flow. That's an exceptional hurdle for any AI system.
It sounds like it's not just a technical hurdle, but maybe almost a philosophical one for AI. Why has achieving this kind of rigorous step-by-step proving been so, well, elusive until maybe more recently?
Well, historically, it requires not just intelligence, but a kind of absolute precision and ability to navigate these huge logical spaces without making a single error.
Okay.
We have seen some impressive advancements lately, though, like DeepMind's AlphaProof and Alpha Geometry. They showed AI systems getting to International Math Olympiad, IMO, medal-level performance.
It is a huge step, no doubt.
A significant step, yes.
But if we look at the bigger picture here,
Right.
many of those successes and even other open source efforts like, say, DeepSeek-Prover-V2, they often rely on just massive models, right?
Huge models.
Like DeepSeek-Prover-V2 has 671 billion parameters. That's just colossal. Or they need incredibly intensive computation during inference, like when the model's actually trying to make the proof.
That's right. A lot of compute power.
So it really raises this question: can we actually get top-tier performance without needing such, immense resources?
And that's precisely the challenge Goedel-Prover-V2 is tackling head-on.
Okay, so this is where Goedel-Prover-V2 comes in, a new series of open source models. They're not just hitting state-of-the-art performance, but doing it with incredible computational efficiency.
Yes, efficiency is key.
Their mission seems to be advancing formal theorem proving without needing these gigantic models or vast computation, or, importantly, proprietary tech.
Yeah.
So how? How are they actually pulling this off?
Okay, let's unpack it. Their approach really involves three key innovations. They span the framework, the data strategy, and the training methodology.
Three key things. Got it. What's the first one?
The first innovation, and it's quite powerful, is called Verifier-guided self-correction.
Verifier-guided self-correction.
Okay. So unlike informal reasoning, where you might just, spit out an answer, formal proof generation can use immediate feedback from proof assistants like Lean.
Like the Lean system itself tells the AI if it made a mistake.
Exactly. Think about how humans learn, right?
Right.
We try a proof. Maybe a teacher or a compiler tells us where we went wrong, gives us feedback on errors, and then we revise. We fix it.
Makes sense.
Goedel-Prover-V2 essentially formalizes this intuition.
So the model is getting coached, almost, like a student getting precise feedback on its errors. What does that corrective guidance actually look like for an AI?
Yeah, that's a good way to put it. After an initial proof attempt, any verification failures, places where the Lean checker says, nope, that's not right, are precisely parsed.
Okay.
The specific error messages and information about why the proof failed are fed back to the model. That's the corrective guidance.
I see.
The model then uses that guidance to generate proof repairs. It tries to fix its own mistakes. This leads to an iterative self-correction process.
So it tries, fails, gets feedback, tries again.
Exactly. And this isn't just a minor tweak. It seems to be a real paradigm shift for AI theorem proving. Goedel-Prover-V2 effectively learns how to learn from its mistakes in a way previous models just couldn't. And that's key to its efficiency and tackling complex reasoning.
That sounds absolutely foundational. And speaking of foundations data, our sources mention that even existing Lean datasets, like one called Goedel-Set-V1, had pretty big quality issues.
Oh, definitely.
Human evaluation found that over 80% of the unsolved problems in these datasets were actually incorrectly formalized. What does that mean? Incorrectly formalized. And how do they fix such a huge data problem.
Right. So incorrectly formalized means the original math problem written in natural language wasn't accurately or completely translated into the precise machine-readable format of Lean.
Ah, so garbage in, garbage out, basically.
Pretty much. It's like having a perfect recipe in your head, but writing it down with the wrong measurements or missing steps. You just can't cook it right.
Okay, so how did Goedel-Prover-V2 address that?
This leads to their second big innovation, scaffolded data synthesis. They generate high-quality training data in two main ways.
Scaffolded data synthesis. Okay, so they're building better foundations. How?
Well, the first way is through formalizer training. They actually trained their own formalizer model called Goedel-Prover-V2.
So an AI to help the main AI?
Kind of, yeah. This formalizer model excels at translating natural language math problems into Lean code. It apparently incorporates reasoning capability itself. They kicked it off by prompting Claude Sonnet 4 to generate about 50,000 formalized statements.
Wow.
And this Gödel Formalizer V2 significantly outperforms previous formalizers. It's all about getting that input perfectly precise for Lean.
Okay, so that's one way to get the translation right. What's the second method for generating better data?
The second is formal-based synthesis. This is really clever. If their main prover fails on a hard problem,
Yeah.
it leverages that failed attempt to generate simpler related problems.
How does that work?
They use a specific command within Lean, a tactic called extract goal. This lets them pinpoint and isolate the specific unsolved parts of the bigger problem, the sub-goals it couldn't crack.
Ah, so it breaks down the failure into smaller, learnable pieces.
Exactly. It turns a failure into a new targeted learning opportunity. Those unsolved sub-goals become fresh training data. It's brilliant because it creates relevant, challenging, but maybe solvable problems right from the model's own struggles.
That is smart, turning dead ends into new paths.
And it even includes generating negations of statements. So the model learns to recognize both true and false propositions, which is important for robust reasoning.
Okay, so generating problems from formal failures.
Hmm.
Do they also generate problems from the informal side, like from the natural language descriptions?
Yes, that's the third part of the data strategy, informal-based synthesis. Here, they use other powerful large language models like Qwen 332b to generate variations of math problems in natural language, some simpler, some harder. These new natural language problems are then fed through their formalization pipeline using Gödel Formalizer V2, and then they're meticulously filtered. Another LLM checks them for correctness and difficulty to weed out trivial stuff or things that are just wrong.
It sounds like an incredibly thorough process just to get the training data right. Quality over quantity, it seems.
Absolutely foundational, especially if you want efficiency. You can't afford to waste compute cycles training on bad data.
Right. Now that brings us to the third innovation, model averaging. You mentioned this addresses a common challenge where, later in training, a model's output diversity can decrease.
That's right.
So it gets better at maybe one specific way of solving things, what you call pass at one, getting it right first try, but worse at finding multiple different correct solutions. That's pass at n. Can you quickly clarify pass at n again?
Sure. So pass at n basically means the model gets n attempts, n tries, to solve a problem. If any of those n attempts produce a correct proof, it counts as a success. So pass at 1 is success on the first try. Pass at 32 means success within 32 tries. Higher n gives the model more shots. The problem is sometimes models get really good at pass at 1, but lose the flexibility needed for good pass at n performance.
And Goedel-Prover-V2 uses model averaging to tackle this. How does that work?
They essentially merge different stages of their model's checkpoints. Think of it like blending snapshots of the model taken at various points during its training. They average the weights.
And what does that blending, that averaging, actually do for the model?
Well, the research and their observations confirm it significantly improves the feature diversity of the final model. It helps it retain different ways of thinking, you could say.
Ah, so it keeps its options open, strategy-wise.
Exactly. And this effectively enhances pass at n performance. It's especially helpful for the self-correction capabilities we talked about, because self-correction often relies on trying alternative paths.
Okay, wow. Verifier-guided self-correction, scaffolded data synthesis, model averaging. That's quite a toolkit. I'm really curious now, how does this all translate into actual performance? What do the numbers say?
The results are quite remarkable, frankly. Let's look at MiniF2F, that's a benchmark of high school level math competition problems.
Okay.
Goedel-Prover-V2, the 32 billion parameter version, hits 88.1% accuracy at pass at 32.
Pretty good.
But then, with just 2 rounds of that self-correction, it jumps to 90.4%.
Nice bump. How does that compare?
Well, put it in perspective.
Yeah.
The previous state-of-the-art was DeepSeek-Prover V2,
Yeah.
the 671 billion parameter one.
The giant one.
Yeah, that one achieved 82.4%. So Goedel-Prover V2 32B is significantly outperforming a model more than 20 times its size.
Wow. That's huge.
It gets better. Even their smaller 8 billion parameter version of Goedel-Prover V2 hits 84.6%, still better than the 671 billion DeepSeek model.
That's astonishing efficiency. What about on harder problems, college level?
Right, so on PutnamBench, that's a more challenging college-level benchmark. The 32B Godel model solves 43 problems straight up. That's nearly double the 22 problems solved by the huge DeepSeek-Prover V2 under the same compute budget.
Double it.
And with self-correction. The Godel model solves 57 problems at pass at 32. And if you give it more attempts, at pass at 184, it solves an astounding 86 problems. That puts it firmly in first place among open source models on this benchmark.
Incredible. They also mentioned creating a new benchmark.
Yes, Math Olympiad Bench. 360 human-verified Olympiad-level problems. They created it because they found issues in other benchmarks, like MiniF2F, sometimes having incomplete problems or mismatches between the natural language and the formal lean code.
So they're really pushing for rigor everywhere, even in the testing.
Seems so.
What really leaps out from these numbers, though, is the clear impact of that verifier-guided self-correction. You see it adding, what, around 2 percentage points on MiniF2F, and leading to 14 more solved problems on PutnamBench just at pass at 32. The paper mentioned ablation studies, too. Did they confirm this?
Yes, the ablation studies where they systematically disable parts of the system to see what breaks confirmed just how vital these feedback mechanisms are. Things like using the specific compiler error messages from Lean, and also retaining the chain of thought, the reasoning steps from previous failed attempts, were shown to be crucial for the self-correction to work well.
It's not just that it failed, but how it failed.
Precisely. This also highlights something they call sample-efficient inference.
Sample-efficient inference. What does that mean in practice?
It means that unlike older models that often needed massive sampling budgets, like trying hundreds or thousands of times, essentially brute forcing or needing complex reinforcement learning during testing.
Right.
Goedel-Prover-V2 reaches very high pass at N accuracy with relatively minimal inference overhead. Often just N32 or N64 attempts are enough to get close to its peak performance.
So if I'm getting this right, it's not just throwing darts hoping one hits the board. It's learned to be a much better dart player, so it needs fewer throws.
That's a great analogy. It indicates the model really internalizes powerful reasoning strategies during training, rather than relying purely on massive search or compute power at test time.
This really hammers home that central question. What does it mean that these relatively smaller, more efficient models can actually outperform the colossal ones?
Well, it strongly suggests that smart training, clever data strategies, and innovative architectural choices like self-correction can truly challenge that bigger is always better assumption in AI.
It's not just about scale, it's about smarts.
Exactly. Smarter design can beat brute force, at least here.
So bringing this all together, what does this mean for you listening? Maybe you're prepping for a meeting on AI, diving into this field, or maybe you're just, incredibly curious about where AI is heading.
I think the big takeaway is that Goedel-Prover-V2 clearly demonstrates that the frontier of formal theorem proving can be pushed significantly forward without needing access to, incredibly large models or vast computational farms or proprietary closed-off technology.
And it's open source.
Critically, yes. Its open source nature means this isn't just some finding locked away in a research paper. It's a practical, efficient platform that anyone in the research community can actually grab, use, and build upon. It really accelerates progress for everyone.
This whole deep dive really shows how combining these clever ideas, the iterative self-correction, the smart data generation, even things like model averaging can push AI into realms we once thought needed just immense scale. It really makes you wonder how much more efficient AI can become.
And consider the ripple effects. If AI can be taught to rigorously prove complex mathematical theorems with this kind of increasing efficiency, what new possibilities does that unlock? Think about other domains that demand absolute logical certainty.
Like what?
Well, drug discovery, designing new materials perhaps, verifying complex software systems to make sure they're bug-free, validating the safety of autonomous systems, anywhere that logical correctness is paramount.
It really does get you thinking, doesn't it, how AI might eventually bridge that long-standing divide between our sort of intuitive human reasoning and the world of rigorous formal proof verification. It's quite a provocative thought to maybe mull over.